hardware-oriented talk in this workshop. Uh, so what I'm going to talk about is using a form of computing called stochastic computing. I'll briefly talk about what it is and why is it suited for machine learning at the edge. So if I look at, in context of hardware, and if I'm doing machine learning, where does the energy really go? And this is, some version of this plot is very popular, right? You'll see that, okay, the energy it takes to read 32 bits from DRAM is about 640 picojoules. To read the same amount of data from a local SRAM is about 5 picojoules. To do a multiplication using these two operands and storing the result just takes 0.8 picojoules. Do an addition, much less. So there is at least an order of magnitude of energy difference from doing local compute, and 2 orders to 3 orders of magnitude energy difference from doing a read from a distant memory and then doing compute with it. So what this tells you is why, and by the way, most machine learning boils down to these two operations, right? So there's so essentially this is what we care about, but the native arithmetic units don't consume as much energy. It's the getting the data in and data out which takes up most of it, right? And that's what. And as the amount of data that needs to come in and come out has been increasing, this problem is becoming worse and worse. So with that as a background, I want to first give a very quick tutorial on what is stochastic computing. It's a very, very old concept from 1960s. The idea here is you represent a fraction by the number of ones in essentially an infinitely long bit stream. So for example, in this case, if I take a 10 long bit stream, if 8 of them are ones, 2 of them are zeros, I call it as representing 0.8. Okay. Why is this so interesting? Because if you now take a single little AND gate and feed 2 of these stochastic bit streams as an input to it, the output of the AND gate will be probability of A multiplied by probability of B, which is basically the stochastic bit stream output of multiplication. Now, if you put an OR gate after this, you can show that that roughly translates to A plus B. So now, this simple one AND gate, one OR gate becomes a multiply accumulate unit. And this remains a multiply accumulate unit whether I want to do 4-bit arithmetic, 5-bit arithmetic, 6-bit, 8-bit, 10-bit. All I need to do is feed it longer and longer streams to get more and more precise, right? So, and that's what makes stochastic computing fairly interesting. You can show that it can be anywhere from 50 to 100x smaller footprint than a conventional fixed point or int4, int8 style MAC unit. Okay, so you get very high density, but there is, of course, a reduced precision because the length of the stream that is required to achieve precision scales exponentially. So 8-bit stream roughly would require order 256 long stream. 16-bit it would require very, very long stream. So this is well suited for low precision arithmetic, not very well suited for high precision arithmetic, which is still nice because we are increasingly dealing with heavily quantized ML models anyway. Okay. So there are 2 forms of stochastic representations. One is bipolar, so it can represent both negative and positive numbers. The other is unipolar, which only represents positive numbers. What we use in most of our hardware is a unipolar arithmetic. So if you want to do negative numbers, you basically flip the sign and do a second pass. One of the big problems in stochastic computing has been that it requires a random number generator, right? So the quality of the result depends on how random the input bit streams are. And this number is sometimes called as an SNG or stochastic number generator, which will take a integer value or a fixed fraction value and convert it to a bit stream. And the kind of simple way to do it is you just put a random number generator with a buffer storing the value and do just a comparison, and that will output that stochastic bit stream. Right? But these things can be somewhat expensive. because generating good quality random numbers is somewhat expensive. Now, what works in our favor in case of machine learning is that once you generate the number, the fan out or the reuse of that generated sequence is very, very high. You use the same weight or input value tens, hundreds, thousands of times. So this generation cost is heavily amortized. Skip this. Addition, there are, as I mentioned earlier, a simple AND gate works as a multiplier. Addition, there are a couple of different ways of doing it. The most common accurate way is putting a multiplexer. Now, the problem with multiplexer is it does a scaled addition. So as a result, if your stream length remains fixed, you essentially get underflow problem very quickly. And that is not very useful because you're trying to do very, very long dot products in case of machine learning. Right? You could do an accurate addition, which is basically put a counter and just add them. Right? That's also not so great because then you're losing half the benefit of stochastic computing. What we use is a modified addition, which is an OR gate, which essentially does, if you plot this out, it looks like a saturating adder.
Sorry, basic question.
Yes.
It assumes that all our computations are for numbers between 0 and 1, right? How do you...
Yeah, so that is just you scale the numbers first, right? So once you get a number, let's say integer, you first scale the numbers, and then everything is a fraction between 0 and 1. Right. So this is essentially a saturating adder, and this is what we use because this works out much, much better because you don't get into other numerical issues. Other operations, there have been like decades of work on how to implement other more complicated operations in stochastic computing, but very rarely are they useful because they use complex finite state machines, all sorts of things, and at that point it becomes like almost pointless to use stochastic computing because they're too complicated. Okay. So why we believe that SC would be a good option for edge machine learning is because of this very dense implementation of multiply accumulate, we can do very dense linear algebra, which is what SC requires or ML requires, and most ML models have a somewhat reasonable tolerance to approximation, right? So, and then the question becomes, how do we build an accelerator that takes the best advantage of SC? So where would the advantage come from? So one thing I want to emphasize is if I do 8-bit multiply addition or anything like that, the benefit in energy per se of the native operation is not very high with SC and conventional arithmetic. Where the benefit is coming from is the size of that multiply accumulate unit is 50 to 100 times smaller. So I can pack many more of them in the same chip area. If I can pack many more of them, I can get much more input, output, and weight reuse. Right? So, and as I said earlier, what matters in context of energy efficiency of ML is how much can you reuse the data once you have read it from memory. So here, if I have many, many more, 100 times more multiply accumulates available, I can reuse the data roughly 100 times more. And that's where the energy benefit largely comes from in case of stochastic computing. So I'm not going to the exact details of the architecture, but the idea is that the whole architecture was done to optimize or maximize activation, weight, and output reuse. It has very, very high compute density. We can pack about 100,000 max per millimeter square. And that enables having much larger on-chip SRAM buffers, which again helps with reducing DRAM accesses. It has a small little ISA to program it. So how well does it work? On the top, I'm showing just some accuracy results of on 2 different data sets on 4 of SC versus 4-bit int4 and int8. And so we can, depending on how you design it, you can get roughly int4 equivalent or int8 equivalent accuracies with the SC. The and the frames per joule or frames per second, kind of think of it as a throughput metric or the energy efficiency metrics, they are 10 to 100x better than corresponding dedicated digital accelerators. So IISc is a very famous digital accelerator out of MIT, and we're just comparing it with that. So we get about 5x faster and 2x more efficient at the same time, compared to a dedicated digital ASIC. And this is the actual chip that we had built and taped out and measured. Okay, so that was introduction for very generic convolutional neural network type accelerators. Next, we wanted to look at what happens if the data happens to be sparse. And the use case that we looked at is event-based vision. So those of you who may not know it, I'll first give a quick intro to what event-based cameras are. So the camera that we are all used to are framing cameras, right? They will take a picture or series of pictures, and they usually have a frame rate of 60 frames per second, 100 frames per second, etc. And so as a result, it's very difficult for them to capture fast-moving changes. Moreover, in fast-moving changes, you see this blur. I mean, we've all probably, whenever you've taken a picture, you probably have seen it at some point or the other. And also, they suffer from very poor dynamic range. So it's very difficult for those sensors, framing cameras, to capture something which is very bright and very dark at the same time. And this is where event-based cameras shine. So event-based cameras, what they do, instead of capturing the whole scene, they only capture the changes in the scene. So essentially what they're doing is you take a scene and every sample is just telling this pixel went up or went down in intensity, right? You could integrate that over a period of time to construct a frame, but that's not the point here, right? So you get essentially, depending on which event camera you use, either you get like 0 + 1 or +1 -1 output. The sampling rate of these pixels is very, very fast, order a single microsecond. So they implicitly filter the background out, but you get a very, very sparse generated output. Okay. One popular one is from this company called Davis. So what are the challenges in processing these events, right? The biggest challenge is the number of events you need to process is upwards of 100 million events per second, right? So, and keeping up with the generated camera becomes a challenge. And again, if I look at even in the SC example and look at where does the energy go in forming the compute. So if I process the things naively with dense and sparse, most of the energy pretty much remains the same. I might save a little bit in the mag because I'm shuttling zeros here and there, but again, not a big deal because I'm still spending energy in clocking, flops, memory access, in case this was an analog accelerator, so even the ADC, etc. So unless I can actually leverage sparsity directly, just throwing sparse data onto a normal digital accelerator is not going to be of much use. And that's a well-known problem. Dealing with sparse matrix multiply is very, very hard for digital systems. So the one key thing where SC helps us in doing the sparse compute is, remember, you're feeding a stream of bits. At any point, I can cut the stream and I'll get a gracefully approximate answer. Right? So if I'm feeding lots of zeros, and let's say to get a reasonably accurate answer, I need 256 long stream. If after 64 long stream, I see answer is still 0, with fair degree of confidence, I can say that one of the inputs was 0. Right? So, and that's what SC buys us. So we use this technique called early termination, which basically, as the stream is being processed, we keep track of what's the current state of the output, and based on that, we can terminate the computation early. So, and this early termination can be used for other things as well. application we were interested in here was object tracking. So in that case, usually you're tracking maxima of certain pixels. So if certain value is much, much larger than the others, you can terminate everything else because you kind of know where is the maximum at this point. So you can terminate per output, per filter, per region of interest, etc., and it implicitly skips regions with high sparsity. So we get about a factor of 2 kind of latency reduction if you have about 98% sparsity in the input or the weights. Yes?
Sorry, I don't understand what do you mean by sparsity.
Well, sparsity is, let's say I'm doing multiplication of 2 matrices. If there are lots of zeros in either of the matrices, then when I'm multiplying, I'll be multiplying 0 with something. Right? That's a pointless exercise. Right? But leveraging, knowing where the zeros are, compressing the compute is very, very hard for conventional digital accelerators. That's why if you look at sparse matrix multiplication algorithms, the point at which they're actually faster than dense matrix multiplication is when the sparsity is upwards of 99 point something percent. Because the effort required to detect where the zeros are is more than just doing the operation itself.
This is small doubt. There are already formats like CSR.
Yeah.
So, I mean, is there any particular advantage when it comes to SC wherein?
So CSR is just a storage format.
Right.
So it doesn't do anything else. CSR is just allowing you to little bit more effectively store sparse data. Right? It has nothing to do with compute. It's nothing to do with. It reduces your memory accesses a little bit.
Okay, so it's just taking care of the memory, but the compute.
Compute is still the same.
Okay.
Yeah. So CSR is, as I said, just sort of a sparsity aware storage format, and yeah, all GPUs support it in some form or the other. So again, I'll not go into the hardware accelerator design itself per se more, but that gives you. So this is the kind of the block diagram of the chip we have taped out. It tries to do this stochastic computing inside an SRAM cell. I'll not go into the circuit details of that either. But roughly in a small little chip, we are able to pack about 160,000 multiply accumulate units. And it's about 64 kilobits of SRAM on it. It supports a stochastic number generator, which is embedded within the SRAM. Of course, there's a very dense MAC array, and there's early termination to deal with sparsity. So it can process about 270 million events per second, and roughly efficiency translates to about 160 odd tops per watt. So how does the tracking work? Again, the tracking algorithm is nothing new. It uses Gabor filters, which are basically directional filters, and it clusters them, then generates bounding boxes. Then there's a well-known tracker called Norfair, which is used for tracking. So there is nothing specifically new in this. The only thing I wanted to point out is we profiled it on running this tracking algorithm on a GPU. About 80% of the time goes in doing the filters themselves. And that's what we're trying to speed up using stochastic computing. So here, basically, each filter is space and time both. It's x, y, and time dimension, just to clarify. Here could be an example scene. You're capturing something from let's say a drone or something, and you put an event camera that gives you these sequence of events. Most of it is very, very sparse, and you get a couple of pixels triggering every time to say if there are changes or not, right? And this is giving you a rough sparsity map on an example ROI of how much the sparsity is very, very high in these outputs of event-based cameras. So what we can get, so this is actual 12 nanometer chip that we had taped out and measured, and we can get anywhere from 270 to 730 million events per second that we can process on this small little chip. The state of the art at this point before that was about 11 million events per second. So it's about 20x at least or more faster in terms of throughput than anything else. And with and without early termination, we get about a factor of 2 to factor of 3 improvement in the throughput. How well does the tracking work? This is an example data set where you're tracking a flying object over about a half a second, and events are accumulated in 2 millisecond intervals. And the black is the ground truth, how the object is moving. Red is tracking without any early termination, and blue and green are tracking with different degrees of so-called early termination. And in a 640 by 480 camera, the pixel error is less than 5 pixels in terms of where the object was located. So that was an example of where we could use SC, where conventional digital systems will have a very hard time to keep up with it. So the next challenge, which I have so far glossed over, is the software side of SC, or in general approximate computing. So when I look at machine learning models, right, our mental picture is I'll plug a model from Hugging Face, maybe I will run a quantization in PyTorch, and I'm ready to go. And that model unfortunately breaks down if you use any form of approximate computing, because post-training quantization is very, very difficult for most approximate computing regimes. Your multiplication can be approximate, your accumulation can be approximate, and the error could be input dependent as well, depending on the underlying approximate hardware. So here's an example of an approximate multiplier, and so it makes error in one entry in the truth table, and for some reason that switching this entry to a different entry dramatically speeds up the multiplier, right? So that's the incentive to do it. But now imagine if you build a large 8-bit or 16-bit multiplier using these units. The nature of where the error is going to be very, very complicated. And modeling it in any compact form is very, very hard, right? So analog computing, like there have been lots of papers on using analog arithmetic for energy efficiency, etc. They face similar problems. You have analog to digital converters. They have range and precision issues. Stochastic computing that I just talked about, it has random bit stream errors in the input. You have effectively a nonlinear accumulation because of the a plus b minus ab setup, right? So there are lots of reasons why approximate arithmetic, though looks good on paper, it's very, very difficult to make it work. And so what we started to look at is how will you train models for approximate computing. So first, let's see if I don't train, what happens, right? So if I just take a pre-trained model for int 4, int 8, etc., and just run it on approximate hardware, what happens to accuracy? So this is an analysis, I forget which data set and model it was, but you get about, if you use the approximate multiplier that I just showed, you get an 11 percentage points drop in accuracy. If you use analog accelerator, you get about 20 percentage points drop in accuracy. If you use one of our stochastic computing accelerators, you get about a 50 plus percentage points in accuracy, which basically means it's useless. So we have to address this, right? So we can't take a pre-trained model, run inference directly on it. So you have to train, or at least some form of fine-tuning before you can run it. Now, what's so challenging in doing the training / fine-tuning? The challenge is modeling of the approximation is very computationally intensive. So CPUs or GPUs don't have native operators for approximate arithmetic, right? So you're basically emulating them every single time, right? So, and here's an example of how much time it takes. So if I take floating point, if it's normalized to 1 unit, 0.5 for multiplication, 0.5 for addition, let's say, roughly. Then if I use stochastic computing and unroll it with 64 long bit streams, it takes me about 64 cycles. If I do approximate multiplication to emulate it, it takes me about 86 cycles. If I do analog computing, multiplication is fine, but addition takes about 9 cycles to emulate it, right? So this, if the native operations are slowed down this much just by emulating, the whole training process slows down by roughly that factor, right? So, and that's not the, yeah. So that's the first part. The other part, which is also important, is when you are using these pre-trained kernels from PyTorch, cuDNN, etc., they're very heavily optimized. If I want to, even if I'm willing to pay this, let's say, 1x or 9x penalty, the actual penalty is actually much, much higher, because to model the addition as an analog addition, you will have to break up the underlying gem kernels to separate multiply and additions. You'll have to do addition by your own custom kernel and then repackage things. And the effective slowdown can be easily 2 orders of magnitude. So what that means is, that's why if you carefully look at papers which talk about approximate computing based accelerators, they still talk about MNIST as a data set and really, really tiny models, because it's scaling the training is just very, very hard. So that's what we try to focus on. So the first trick that we place, so when I'm doing a forward pass during training, right? And in backward pass, I'm propagating the gradients, right? So in case of stochastic computing, for example, my addition is a plus b minus ab. So unlike a conventional addition, I have a partial derivative with respect to the operations, right? So what do I do with this? Because if I want to preserve this partial derivative and propagate it, I will have to break up the adder into a separate operation in the backward pass. And that I said earlier that slows down things dramatically. So because if I break it up, I slow down the entire training process by 100x. So what we do is what I showed here. We create a proxy activation to model this nonlinearity. So essentially, in case of and that proxy activation is custom designed to nature of the approximation. In case of stochastic computing turns out to be something that looks like 1 minus e raised to power minus something. In case of analog arithmetic, it looks like something else, etc. But you design a proxy activation function during the backward pass, and that's what is used in training rather than emulating the underlying operators themselves. And that recovers that roughly factor of 100 slowdown that we saw in this training. And these are cheap, relatively cheap to implement. These are pointwise functions, it's activations, right? And you can still continue to use those well-optimized cuDNN kernels. The forward pass is a similar issue, right? So in the forward pass, again, we do not want to emulate the approximate arithmetic. So what do? We look at the distribution of errors and kind of a mean and a sigma and the distribution itself. And the mean is adjusted in the activation function, and the sigma is adjusted by injecting noise with similar distributions. And so these are fit to the nature of the error that you already have in the modeling. And this can be done for whether it is stochastic computing or approximate arithmetic or analog hardware, etc. The last part that we do is a well-known technique as well. This is nothing that we invented. It's gradient checkpointing. Here, the typical setup is that when you're training a model, is for every layer you have to buffer or you have to store the activations, right? When you're in forward pass, you have to store the activations for every layer so that in the backward pass, you can use them to propagate the gradients, right? By doing what we did, we are adding many more layers, right? Those additional activation functions are effectively new activation layers. So if they're new activation layers, now I have to store many more activations, even though computing those activations is dirt cheap. So what gradient checkpointing as a technique does, it says, well, these layers are cheap to recompute, so I will not bother storing the activations so that I don't waste memory, and I will recompute them during the backward pass. Right? So that's what we do here as well. So basically, instead of storing computed activations for these cheap activation functions, we recompute them during backward pass. And that allows us to support bigger batch sizes and larger models as well during training. So how well does it work? So for all the three cases that I talked about, having a digital approximate multiplier, having an analog computing substrate, or stochastic computing, we get roughly 5x to 250x speed up in time to train. And the big thing is, this is what enables us to train at least reasonable sized models, even for edge. Before doing this, so this is just showing you the accuracy without improvements and with improvements. They are very, very similar. And before applying all these tricks, we could never even train a ResNet 18 on an IntelliJet dataset. It was just too large on a single RTX 3090. And this allows us to train these larger models at this point. So just to conclude, stochastic computing by itself has some interesting properties that can be very relevant for resource constraint acceleration. It has very low area footprint and cost. It has excellent energy efficiency, very low latency. It supports variable precision on the same exact hardware. It naturally handles sparsity. And if you implement it as compute in memory, the actual compute in memory, those of you who are familiar with how it works, it does not require an ADC, analog to digital conversion, which is one of the biggest pain points of compute in memory. Approximate nature of it is always a challenge, and these training tweaks that we have developed, we are hoping it will help with that. So I think that's where I'll stop, and if there are questions, I'll be happy to take them.
Can you treat the approximation error as a noise and use the regularization technique during training to obtain?
Yeah, so we tried that. I mean, this is roughly trying to do that, right? Here we are injecting noise in the activations themselves during training, rather than adding a regularizer term. Because regularizer term is at the very end. You're not modeling each operation separately. So here we inject a noise which is in some cases somewhat input dependent as well. So instead of regularizer term, that's what we do here.
Instead of improving on the software aspects of the model training, is there a possibility that we can have a completely new architecture based on stochastic computing that can maybe have better trained models to begin with?
Yeah, so that's a kind of a perpetual question for anything that is not GPU. There is a lot of hardware, not just stochastic computing, which would love it if there were custom models which were very tailored to them. It never works out for the simple reason that the world works on GPUs. So whether it is stochastic computing, compute in memory, photonics, there are like lots of techniques that people have proposed. And unfortunately, there is just not enough critical mass behind them for people to try to develop custom models for those still emerging hardware.
What does exactly mean by critical mass here?
Critical mass means enough number of people who would want to use it, right? So you have a million people developing for GPUs, you have like 5 or 6 developing for stochastic computing. There's a big difference, right? So that's where it's very challenging to support enough of a research ecosystem which develops custom models.
Okay, it's usually observed that in neuromorphic computing there is already a lot of sparsity, and then that fits well with this architecture you've proposed. Were there any experiments you did with neuromorphic, like SNNs, and like were you able to see any sort of an improvement when compared to other deep learning models?
So SNNs is not exactly this, but it's somewhat connected. And I'll go back to the same issue which I was just mentioning of why. I mean, SNNs have been around for 30 years. I don't know of a single commercial system which uses SNNs, and there's a reason for that. And so, at least what our feeling was that if we develop custom hardware, it has to be able to run standard models. There have been approaches which have been developed in recent years which try to map conventional models to SNNs, but then it starts to kind of give up the main benefit that SNNs have, that asynchronous nature of operation.
What are some of the ways in which random number generations work? Like, what are some of the algorithms that are used?
So the most common algorithm, digital one that you can do is feedback shift register. Right? You just have a linear feedback shift register, generate pseudo-random numbers. That's kind of a very standard way. It's a small little digital block. You can do it. Of course, you can do, if you want randomness guarantees, there are a whole slew of other random number generators which try to leverage some stochastic noise in the underlying hardware. And there's like lots of them. So.
Sir, in the gradient checkpointing slide, you said that for cheap activation operations, you recompute the gradients. So that implies for expensive, you store.
Yeah.
So what is the ratio of these operations that you usually come across, cheap to expensive?
So in our case, we increased that ratio, right? Because we added these new activation functions, which are very cheap to compute. And that's where we used it mostly. So I don't remember the exact numbers, but I think it cut down our memory footprint by about a factor of 2 by doing this. By the way, this is not a new technique. You can, it's a single flag in PyTorch. You can do it today. So it's just about picking where you want to checkpoint, where you don't, right? So if you're running short of memory, but you're willing to spend more training time, a little bit more training time, this is not a bad approach.
So just this operation did speed up the...
So for us, it was mostly these activation functions.
Okay.
Right? So that, remember in the backward pass, we have these activation functions in the and then those are the ones which we replaced by, instead of storing the activations, we recomputed them. And the activation functions are point-wise, relatively simple to calculate. So that's what we studied. Yes.
So this is a different way of computing altogether, and trying to emulate it sort of loses the advantage. So I was wondering if the weights and biases could be represented as parameterized RNGs in the hardware. Then applying the gradients to this would be simply as we do the reparameterization trick. I mean, that could be a different way of the training thing instead of emulating the hardware.
So what we tried to get around was not to emulate the hardware because that is too expensive. And that's where all these tricks about error distributions, proxy activations, etc., they came into play. Emulating the hardware was like 100x slower at least. And if you start storing the full RNGs, then you quickly run into memory requirement issues as well, right? Because you're storing, instead of, our streams are packed bits, right? So instead of storing 1 bit, if you store the whole stream representing the integer, now I'm using up much more space in the memory. So even that doesn't work out that well. So we store as compressed fixed point throughout the training, and modeling for the stochastic streams is done using these other tricks.
What do you actually mean by error injection?
Oh,
Like what type of error injection?
so error injection is just looking at what, if I do the multiply accumulate, I will get a error compared to the ideal int 4, int 8, whatever value, right? And the error injection is just looking at what that distribution looks like, and instead of emulating stochastic operations by int 4 or int 8, it will inject errors following the same distributions. So you compute the activation, add a random number which follows a certain distribution, which is pre-calibrated from whatever approximation you're doing in the forward pass.
Then why can't we use the original data only instead of
How do you compute the original data?
like the one we are approximating by using SC, right?
No. So when you're training, your underlying arithmetic is still accurate, right? That's running on a GPU. What I want to emulate is something that will eventually be run on an approximate hardware, right? So I don't know what the approximate answer is going to be, right? So I'm trying to, instead of calculating the approximate answer and using that in forward pass, I estimate the approximate answer by using these error injected distributions.
Any more questions? Yeah, so let's thank the speaker. So let me welcome Day-3 and So Day-3 is an assistant professor at IIT Harvard. She did her PhD from IIT Delhi, and she was a postdoc at NUS. Her area of research is in computer architecture and embedded systems. So welcome, Day-3.
Thank you, Neha. Thank you for the organizers for inviting me. Just let me start the presentation. Just a minute. Yeah. Oh, sorry. Pointer is there. Okay, am I audible? So far you have seen a lot of ML talks and some of the hardware things. So today what I am going to talk is more about how do you have or how do you implement efficient and adaptive inference on a hardware. So basically I am talking about platforms that are resource constrained, low resource devices called edge platforms, right? So there is a quiz for you. So you have listened to so many talks, right? So what is the common characteristic among all these applications? And okay, in terms of applications characteristics. Okay. Yeah. So somebody said data hungry. Yeah. No, I'm talking about the applications. What is the common characteristic? So basically, these are resource intensive, these are memory intensive, these are energy hungry, right? So now, if you want to kind of deploy them at the edge, so the next question is, why do you need edge when you have cloud-based services, right? So you have seen these in the last couple of months, right? So you had a AWS outage, and then somebody's bed was inclined because they were not able to, correct it because the cloud was not available. It was, And then you had a lot of problems because the underwater cable current of the cable of Microsoft is gone, so your latency is very high, right? So these are unreliable execution scenarios. Like, so there might be some applications where you don't want your bed to be inclined like this, and then you don't want the temperature of your bed to increase, right? So you want to have reliable local executions that are also, low latency, right? So basically we have challenges in terms of, like, you have low resource devices, you have resource intensive compute, the application. How do you map them, or how do you kind of orchestrate their implementation such that you are able to do some optimization in terms of throughput, in terms of power, in terms of temperature, and so on and so forth, right? So we will see the common theme of today's talk will be that, like, how do you do different implementations or different optimizations or different ways of orchestrating the application such that you kind of improve some important metric like throughput or energy and so on. Okay, so this is a very simple slide which says about, so how many of you are knowing about these low resource devices that contains multiple accelerators? Okay, so basically like most of you might be using GPUs, large GPUs for training and for doing things, but there are also because AI has proliferated so much that there is a lot of from the vendor, from the company side also, they are making a lot of these new devices and new chips and new accelerators. So nowadays most of these low resource devices also comes with powerful accelerators like NPUs and TPUs and even embedded GPUs, right? So now each one of them, they have a different characteristic. The way their the architecture is different, and then the way the memory is managed for each of these devices is also different. So now the basic difference is how they do the compute, right? So in CPU you just do a scalar multiplication, in GPU you can do vector, and then in TPUs you have a tensor as the simple compute or the compute unit, right? So now what is happening here is, how do you know what is the best thing for your application, and how do you want to kind of map your application such that you get maximize throughput or whatever, minimize energy and so on. That will be the today's theme. And this is something which you might have been seeing, or this is the stack that talks about how from the hardware till the application, what are the things that you can choose so that you can orchestrate your application, right? So you have so many choices to make. It's not easy to know which is the one right for you and things like that, right? So even so if you see, right, you have the choice of hardware, even the choice of the system that you want to, OS you want to use, and then what is the library you want to use, and so on and so forth, right? So in it's not trivial to know that okay, this will be good, this will be bad, and so on and so forth, right? So what do you do? So before, what do you do? So these are something that is very important to consider. These are the challenges that we are now having, right? We have limited compute resources, we have limited memory, but then we also have a resource hungry application, and we also have this power and thermal budgets, right? So how many of you know what is this thermal throttling? Any idea? Any? So basically you have a SoC, right? So SoC has a power budget, and it is modeled, or it is designed to withstand till some temperature only, right? So if it is more than that, 70 degrees is a temperature, then what your chip, it should burn, right? If you don't do anything. So by default there is something known as thermal throttling, where you trigger some action to make sure that that thing doesn't happen, that your temperature does not hit, and then if it is hitting, you are trying to immediately safeguard. So we should not do that, right? And in low resource low form factor devices, this thermal throttling is a very you can quickly hit the temperature very quickly, right? So how do you kind of not have that happen in your SoC, right? So like I said, the common theme for today's talk will be this, that how do you kind of dynamically orchestrate your application such that to the hardware it is running, or the runtime condition it is facing, or the input it is receiving, how do you kind of use these information to do optimal execution to manage these primary metrics, right? So the first thing that we're going to talk about is on a architecture called ARM Big Little. So so how many of you know what is IISc is? I hope all of you know, right? So basically this ARM Big Little is nothing but in most of your mobile phones, right, you see the Snapdragon and your Exynos, right? So these are powered by these architecture, right? So here you have power efficient or performance efficient cores and energy efficient cores. So this small cluster is consisting of cores that are not so powerful in terms of performance, but those are energy efficient, and these cores, which are the bigger cores or the performance cores, these are not energy efficient but they give you good performance, right? So now these two are put together in the same chip, right? And then there is a common cache, and then there is a common cache interface, CCI bus, that tries to take care of the data movement between these processors, right? So now your expectation is you want to simultaneously use all of them. It's given to you in your chip, and then you want to use it to maximize the throughput for your application, right? So let's take a CNN, right? So CNN will be having a lot of layers, right? And most of these layers are convolution layers, right? So you do matrix multiplication with a filter, you input image, and then you go and do the next layer, and so on and so forth till you reach your final layer, right? So if you want to like by default, right? So these sorry. So by default, this particular architecture is ARM based, right? So ARM is giving you an optimized library called ARM-CL, right? That means like how you have this TensorRT for NVIDIA. Similarly, you have this ARM-CL for your ARM systems, right? ARM processors, right? So by default, what it does is it tries to schedule the kernel of each layer across all the cores of your SoC. So if you see here, right, in our case we had 8 cores, we had 4 big and 4 small cores, right? So now this each layer, whenever it is trying to, an image input image is coming, and you have a CNN, and then the CNN is implemented in the as a graph using ARM-CL, and now the layer 1, it tries to execute. The layer 1 is nothing but some convolution layer, right? So now what we had seen is when you do this kernel wise execution, that means sequentially one layer after the other layer using all the 8 cores, what is happening is, if you see here, the performance or the throughput increases as you increase the number of performance cores, that is the big cores. But then the moment you start using the smaller cores, the performance drops or the throughput drops, right? So essentially when you think that instead of 4 cores I am using 5 cores, your throughput should go high, right? Because you are using more number of cores now, right? Initially you are doing only 4, but then now you are doing 4 big plus 1 small, and as you see, right, as you keep increasing the number of cores, you see that there is a degradation in performance or in terms of throughput, right? So do you think why this happens? Any idea?
Communication limitations with the bandwidth probably.
Yeah, so basically as I told you in the last slide, right, so we had this we have a common cache, right, and then there is a lot of these when you try to use all the cores and then the data is kind of split between both the clusters, right, you have a lot of inter-cluster traffic which results in a lot of communication, and then a lot of conflict misses goes to your other clusters cache and tries to kind of get the data, so it increases the time, the communication overhead is more, and because of which you see a drop in the performance, right? So now you have an SoC, you are having 8 cores, but then you are not able to use it effectively because of these problems, right? So what we thought is, okay, fine, the kernel level work or the kernel level strategy is not giving you the performance that you would ideally want, so what you can do to improve this, so that's the thing, right? So then what we decided is, instead of using the entire kernel to kind of split among the cores. So when I'm saying kernel, that is like each layer, right? So this is one layer. This is one layer and this is another layer and so on and so forth, right? So now when I'm saying kernel, the complete layer, all the computations of that layer is kind of scheduled across or divided across all the cores to get the computation done, right? But now what we want to do is, we want the layers not to be kind of divided across all the cores, but then can you do the layer level splitting such that you can have some pipelining possible, in the sense that, so different convolution layers have different requirements. So the filter size is not same for all the layers in your CNN, right? So now you have different layers having different filter size and different output it is producing, right? So now, is it possible to create a pipeline with stages that are consisting only, because if you see, right, within the same cluster there was no problem. You saw that with increasing the number of cores you saw an improvement in the throughput, but then the moment you brought in the next cluster or smaller cluster together, then you started seeing a dip in the performance, right? So now can you do some pipelining such that you do put together cores of the same type, and then you have multiple stages of the pipeline, right? You can have a 2-stage pipeline, you can have a 3-stage pipeline, so that what happens here is, when the image 1's layer 1 is processing or layer 2 is processing, image 2's layer 1 can be processed, because now you have divided the whatever compute you are having into multiple stages, and then you are trying to pipeline your processing of the, go ahead.
How can you make sure that there won't be any pipeline for this? Because as you said, different layers have different requirements.
Yes.
And also, if we can pipeline,
Mm.
that means we are utilizing all of our resources.
So pipeline in the sense that we are trying to find out how, out of the 8 cores, how many stages you can. So in our case we have 8 cores, right? So maybe a pipeline stage is consisting of 3 big cores. So one layer is going to be only scheduled on those, layer 1 of the CNN is going to be scheduled only on those 3 cores, and then the layer 2 will be scheduled on the 3 smaller cores. So we are trying to see how do we find the optimal. So we are coming there, okay? So basically what I am trying to say here is, so instead of doing the complete use of 8 cores for one kernel computation, we now do a layer wise splitting, such that we try to understand whether what is the best possible partition, such that you get your throughput improved for the application that you are running, right? It can be anything, right? So it has to be for any CNN, right? So this particular example shows that compared to what we saw earlier, a kernel level execution, for the same CNN, if you do a layer level splitting where you split into 3 stages and you execute, you see lower number of L2 misses between the inter-cluster misses, and then thereby you are reducing your overhead in terms of the communication, right? So another thing that to note is, if you see here, right, so this is your complete networks breakdown. How do you kind of the time spent on processing what kind of layers? If you see here, right, most of the networks having convolution layer is being used, or that is the heavy computation, like 80% of the time you are only spending on doing the convolutions, the remaining 20% you are or less than 20% in some cases, except for this older network AlexNet, where you had a lot of fully connected layers. But other than this, most of these networks, you see convolution is the topmost or the process intensive layer, right? So, and also this particular whatever picture shows you that as the number of or the layer changes, right? So in this case you have 50 convolution layers. You can see that out of this time, what is the time that particular layer took. So the initial layers are taking more time compared to the later layers, right? So why do you think this is happening? Any idea? No. So basically, if you have say ResNet 50, right, you have 54 layers in that, right? So what I'm trying to tell is, you have out of the 54, maybe 40 are convolution layers, right? So the convolution layer initially, the layer 1, it's taking, it is using or taking more time to compute compared to the later layers. Why? Any idea?
Cold start, warm start kind of thing.
Pardon me?
Cold start, warm start.
No. So basically your image, right? So initially when you are processing your image, the first layer it is trying to do a lot of work, and as you keep progressing the deeper layers, the amount of work that you are doing is kind of reducing. So that is the reason you see that there is a reduction in the the time that is spent on performing the convolution on that layer, right? So this is something we can use, like, so okay, the initial layers are heavy, we need to have more processing capability allocated to it, but the later layers are little lighter, so we can appropriately schedule it, right? So now you have, suppose in our case we had 8 cores, but in general if you have say HB big cores and HS small cores, how will you kind of know how many pipelines are possible, right? So this is number of pipelines that are possible with generic number of cores, right? And similarly, how many design points you will have, like if you, because now you have W layers in your CNN, right? And now you want to make your split such that you have so many possible pipelines. So how many design points you have based on these pipelines, right? So you will have this many pipelines, design points in your exploration, right? So what did we do? We did 2 things. So how do we want to kind of make this split possible? So we first wanted to do a model or build a model that will predict based on some convolution, because we saw that convolution is the major time it takes for processing your CNN, right? The execution time is more for that. So if we speed up that, we will be able to speed up generally the execution, right? So what we wanted to do is it possible, because your convolution is nothing but matrix multiplication, right? J. So is it possible to quantify for different filter sizes and for different input sizes what will be the execution time on different configurations, right? So in our case we tried this on a small board which had 8 cores, and then what we wanted to do is, after getting those details of building a model to predict the time that it will take so much time for so many layers, if this is the configuration, if you use 2 cores, 2 big cores, this will be the time taken. If it is 4 small cores, this will be the time taken. If it is 2 small and 1 big, this will be the time taken, and so on and so forth, right? So if you build a model like that, you could use it in runtime to find out for based on the whatever your characteristics of your application, you can appropriately find out what will be the optimal split, how many, whether you want to split it 3 stages or you want to split it 4 stages, and so on and so forth, right? So basically, how did we do? What was the insight for building this model? So basically, if you see here, this is your input image, something but input tensor, right? And this is your filter, the convolution filter, right? So now what we did is, by implementation, this ARM-CL converts this input tensor into a matrix, and then the filter also into matrix, right? So basically, if you see here, right, so this particular input is kind of converted into this matrix, and this every row here, right, is multiplied with every column of this filter matrix to get your output tensor, right? So now you know what will be the based on the filter size, like this is your rows and this is your columns, right? So based on it, what will be your output feature map, what will be the number of computations you do for your filter multiplication, and so on and so forth, right? So now with this information you have, how you can build a model. So basically, now this is going to tell you, if you have a filter size of k cross m, and if you have an input size of n cross k, what will be your time that it takes to execute, right? So now this is going to be on a single thread, but then in our case we want to do the execution on a multi-core, right? So now you also have to know how do you kind of estimate the time based on this for a multi-core environment, right? So now this is nothing but we fitted a regression model to understand based on the matrix sizes and some parameters how much time it will take for the convolution operation to happen, right? So now based on this, what we did is, so now we know the single core time. Now we want to extend to predict it for the multi-core, right? So in this case, what is happening is, this is how the multi-core execution happens, right? So this is your input computation. So when you are computing this input matrix, right, it is kind of divided into chunks called iterations, and this is based on this parameter called tile size. So this tile size is basically depending on what is the cache capacity of your hardware and so forth. So this tile size is a parameter. So in this case, based on this tile size TS, you divide your input into so many iterations, right? And all these iterations are mapped to one thread, and then these iterations are executed sequentially in that thread, but all these threads are parallel. So this iter 1 is going to be put in one core, iter 2 is going to be put in another core, but this iter 1 contains multiple chunks of iterations. This will be happening in parallel, right? So now if this is the thing, this is a total computation you want to do, how will you kind of predict the multi-core thing, right? So now you know for each iteration this will be the time it takes, that is this part, right? So now when you want to do parallel processing, so you do some kind of model, and then you will be able to get that how much time it will take if you have so many threads. So here this t iter and iter t, these are dependent on the matrix size, the input size and the filter size, right? That's what we had seen in the previous slide, right? So now, okay, we know that now we are able to estimate the time for a single core, and we are able to estimate time for a multi-core. Go ahead.
What was alpha?
So these are some constants that we had fit based on the profiling data that we are having. So these are constants. So now, like I said, initial layers are requiring more power, and the later layers are requiring lesser compute. So in this particular setup that we were discussing, right? So what is happening is, you can see that this is the compute capability ranking. So if you use 4 big cores, whatever time it takes, that is lesser than the time it will be taken. So here this is the fastest possible, and then this is second fastest, and so on and so forth, right? So this is what we had seen in our, and because we're talking about pipelining, right? So pipelining, what is the bottleneck? Which if you have 3 pipe stages, right? How do you decide the time taken by the entire pipeline? Who decides? The slowest stage, right? So now if you want to, the throughput is now determined by the thread that takes the largest time to finish. So that will decide what will be the throughput you achieve, right? So now what we want to do is, suppose let's assume that we have a 8 core processor, and we have this 4 big and 4 small. What our algorithm does is, I'm just giving you a very high level view. The paper contains all the low level views, but I'm just trying to tell you what is happening there, right? So initially we assign each of these cores as one stage, right? So in our case we have 8 stages, because each of these core is now going to be one stage. And then what we do, we first assign all the layers to the first stage, right? And then what we do after that, now we want to balance this work across all the stages, such that the time across all the stages, because that's what we want to do, right? Because the slowest stage determines the throughput, so we want to make sure that all of them finish at the same time, almost same time, right? So initially we put all the layers into one of the pipe stages, and then we try to now do the rebalancing. So now we have moved the whatever the layers which are from 54, we start moving, because 54 is the last layer. So from the last layer we start moving, and we move till the point that both of these stages are now almost balanced, right? Whatever is the most possible balance. So this is the first level. After that we keep on continuously doing this till we try to get the whatever possible balance across multiple stages. So this algorithm iterates, and then we come to one point where there is no further possible improvements, right? And then what we try to do is, with that configuration, is it because you first started with this balancing, right? So initially you had L1 to L54, then you started moving. So in this case, you try to only do the balancing among the adjacent pipe stages, right? So you, whatever you had initially, it was still there, and then at some point you now saw that, okay, no more balance is possible, right? But after this, there will be some sometimes it is possible that if you try to iteratively merge some layers and merge the stages such that your inference time can be minimized. So the algorithm tries to find out, and the merging is only possible between the cores of the similar type, because we saw that inter-cluster problems happening, right? So you try doing whether it is going to help you or not, and then at some point you will converge saying that, okay, yeah, there is no firm, this is the optimal way of doing the execution, right? So by doing this, first by building the model and using the model to do the design process exploration, we are able to find out what will be the optimal point at which you are, how many, at what layer you want to split and what should be the split. So basically with this particular thing, we saw that we were able to somehow improve on an average 30% improvement in the throughput compared to just using one of these existing models, and without any optimization that we have the partitioning of the layers. Without that, you kind of take this much time in terms of this many images per second in terms of throughput, but now you can see that the throughput is little bit improved by doing this partitioning and by overcoming this whatever bottleneck we saw, which was not allowing us to use the complete all the 8 cores. Is there any question so far? Anything? Shall we move on to the next one? Yeah.
Does this percentage of benefit increase with the model type?
Percentage of benefit increase. Yeah, so basically the larger models, when you pipe them, it is more efficient compared to non-piping them. Yes. Okay. So the first one what we saw was how do you maximize the throughput, right? So the second then that we are going to see is something dynamically. How can you kind of change the way that your CNN processing is happening, such that you are aware of the applications, changes in the applications and changes in the environment that you are operating the application. Okay, so for this particular work, what we did is, so we had put some cameras in Delhi, in a place called Lajpat Nagar, and then there are intersections where the traffic is being monitored, right? So basically what we wanted to do is, say they wanted to put these embedded devices on the signals to do this traffic monitoring, and then there are a lot of problems. So first thing we'll see, first thing is, like, because these are powered by the complete power, so it is having problem in terms of how much time you could keep your thing on, your system on, and also environmental conditions like what is the temperature on which you are operating and so on and so forth, right? So what we wanted to do here is, the application that we are trying to work here is in terms of, so we have cameras that are fitted in the intersection, and these cameras kind of do two things. One is trying to check the violations, like whether somebody has violated the speed, somebody has violated the signal, and then it also wants to capture who has violated. So you have to also have a number plate recognition camera for getting the number plates and then doing OCR on that, right? So basically in this particular application, what we had is, we had 2 cameras per intersection, and for each of this camera we had 2 cameras for understanding the number plate. So basically in this case you have like one camera towards the intersection and another one is away from the intersection, and for each one of them you had 2 number plate cameras. So totally you have 6 cameras in one intersection, and you have 24, if you have 4 intersections you have 24 such cameras, right? So you have 24 such feeds coming on to your system parallelly, and now you have, say, one NVIDIA Jetson AGX or NX or whatever it is, right? So how do you now process these 24 threads in real time such that you are not compromising on any of these things, and still you are able to, because these are real-time applications, right? So if you miss some signal violation or your speed violation, your purpose is lost. You are like not able to do your achieving what you want to do. Similarly, if you are not able to capture the number plate, it is going to be wrong, right? So you also have requirements in terms of what is the FPS required, what is the power that you can consume, and so on and so forth, right? You should not miss those deadlines, right? So what we did is to understand the queue, to understand what is the density of the vehicles in that particular traffic frame, we ran some computer vision algorithms. So computer vision algorithms like optical flow and background subtraction, those are not CNNs. Those are just to understand the queue density, like what is the density of the queue in that particular intersection and how many vehicles are there and so. But the actual object detection is done by YOLO or this object detection. So that is CNN based models. So that is running on all these cameras. The that is running on the GPUs of all these inputs from the cameras, and then the CPU is running the background subtraction as well as the optical flow, right? So now this is the task that we have in hand. This is the application that we have in hand. How do we kind of optimize the execution, right? So what we saw is in these are different approaches, like say for example, so this is one approach, this is one approach. Does it work? Okay, so yeah, this is one approach, this is one approach, right? So similarly, we took 3 approaches, and over 40 days we collected data continuously. What we saw is every hour, right? Within, this is like the x-axis is telling you the hour of the day, like this is 7 a.m., 8 a.m. till like night 10 p.m. or so on. Okay, so what we saw is even within the same hour, there is a lot of, the box plot says that there is a lot of variation, right? The traffic is not same, like it's not like every 7 o'clock, every day 7 o'clock, the traffic is very high. In every day 10 o'clock, the traffic is very low. We cannot have such things. If you have such things, then you could just use a static whatever policy. But then this dynamicity in the traffic, that is within an hour you are having difference in the amount of vehicle passing through and the amount of traffic happening. So we want to use this dynamicity to kind of orchestrate the execution such that you are not violating any of these things. Still you are trying to have an efficient way of optimizing your execution, right? So the problems or the constraints here is, as you keep increasing the number of threads, right? Like I said, each of these threads is one input from the camera. So as the number of threads increase, your power will be increasing, because you're doing more work, more power, right? And power is, if you increase your power, temperature also increases, right? So with the increasing number of threads, you can see that your temperature increases, right? At some point it is reaching 70 degrees, and so like I said, after some point this will not work because you have already hit the thermal thing, right? So now this is first constraint. Second constraint is like how your number of threads increases the power. Similarly, frequency, because your dynamic power is alpha CV square F, right? So increasing the frequency will increase your power, which will increase the temperature. So now if you kind of run your GPU always at the highest frequency, what happens? You always consume this higher power, right? So now the question is, do you really want to run your frequency at all the time, this highest frequency possible, and do you want to run all the time with 24 threads, or can you use the dynamicity in the traffic and map your requirements or your controller such that you only spawn that many number of threads in which you have meaningful data, or there is traffic, and those frames or those intersections from where you don't have traffic. Say for example, not all the time all of them are full, right? So some intersection might be fully empty, there is no traffic, but then there are 2 other intersections in which the traffic is coming. So why do you want to run the frames or empty frames that have no traffic? So if you able to know from your density that there is no traffic, then why do you want to run at that particular thread at the, or even the thread processing the empty frames, right? So you could stop the thread and you could only compute or execute the number of threads required based on the amount of traffic that is coming from which particular approach it is coming, right? So by another problem, the third problem is the ambient temperature, right? So basically if you see here, right, if your Delhi's temperature, ambient is the environment temperature is 35, the CPU goes up till 48 degrees. But for the same workload, same frequency, if you run it at 45 degrees ambient temperature, there is a 10 degree increase in the temperature, which will also increase the power, and the kind of, you will hit the thermal threshold much earlier because you are now having. So now these are your runtime changes in your environment. How do you kind of use these information to effectively, orchestrate your execution, right? So in this case, what we did is we have a controller logic in which, based on the traffic density in each of these threads, we try to see how many threads to spawn and what is the frequency. So basically, the problem here is in these embedded devices, right? You cannot have a frequency per thread. There should be some common frequency because there is no so many clock domains. You have only one common clock domain. So now you cannot have a per thread frequency, but you could find a frequency that kind of satisfies the FPS level based on the traffic at that point of time, right? And then we kind of run these controllers for around every 60 seconds once, like a minute once, and then we see whether there's a change in the traffic, and then based on it, should we invoke the change in the frequency, or should we add more threads, and so on and so forth. So this is somehow, kind of using that information that CPU is giving you based on the density and trying to do this orchestration. Alright, so what is the result we got? So we lost some performance because we were not always running at the topmost frequency. These are the so basically, right, so this changing the frequency is called dynamic voltage frequency scaling, DVFS, right? You might have been seeing that, right? So by default, this GPUs have these DVFS based on, so they have their inbuilt DVFS based on the workload the GPU is getting. It will try to kind of fix the GPU's frequency so that it does not run always at the highest frequency. So these are some by default whatever it is available, and this DynCNN is the frequency controller that we have built. And what we are able to see is we are successfully able to reduce the power consumption and the temperature, but we are losing out little on the FPS because we are not always running at the highest FPS possible. But this whatever FPS that we are trying to use, we are trying to not violate the deadlines that what we were asking for based on the, because how this is possible, when you have very heavy traffic, right, the movement of the vehicle is very slow, so you don't need to process your frames at a higher rate. But if the traffic is very less, the speed at which the vehicle goes is very high, so you need to have your GPU run at the highest possible to capture that frame, capture that number plate if it is missing. So that is where your change in the traffic is able to help you find out what will be the optimal frequency and what will be the optimal number of threads that you can use, such that you are kind of minimizing this power and temperature. Yeah.
So are you just sampling like less frequently when there's less traffic?
So we are sampling at every 1 minute. So we saw that for a minute or so, the traffic is almost same. It's not so dynamic, like 1 minute interval. Right. So this one, whatever so far we had seen, we had tried to run only one application, right? So now let's assume that you have multiple applications, right? So you have multiple applications, you have multiple hardware like an NPU, a TPU, a GPU, whatever it is, right? And now each of this hardware is allowing you to run your application. Like quantization is one of the way you can improve your, reduce your model size and improve your whatever storage requirements and so on and so forth, right? So now each of these accelerator is allowing you to run your model with different precisions, and different precisions means with higher precision you have more accurate, but you also consume more power. Less if you use a compressed intent thing, you are having efficiency in power, but you are losing out on the accuracy, right? So now the problem that we are trying to solve is when you are having multiple applications running concurrently, and then you have so many options in terms of which hardware to choose and what precision to run, how will you do it, right? So how will you do it? Any idea? Anyone? I mean, what will be the thing that will come to you first? So this is easy, you can do it without much. So what do you require? So you should first know, right? So when you are having multiple applications, the problem is how, like when I am running with somebody, how my performance is affected, how my power is affected. I mean, like what is the power of the SOC versus when I am running with some other core runner, right? So this is a common problem, like it's a very age-old problem, like how do you model the contention, how do you model. So when you know these are, whatever I am showing is, these are the individual or the isolation runs. When I have the entire thing for me and I am running on a NPU with int 8 precision, then this is the FPS I'm getting, like 21 FPS. But the same network, if I run on a VPU with FP16 precision, we just get only like 4 FPS or so, right? So for the same network, and in this case, right, why do we see this change in the FPS is because when I'm saying these are different hardware, right? So the GPU is from a particular company, the NPU is from some other company, the VPU is from some other company. If you see, right, the VPU is from Intel, the NPU is from a company called Rockchip, the GPU is from a company called Mali. So each one of them, they give their own optimization, they have their own way of optimizing the model, right? So even though the base model, whatever you're running, the tiny YOLO, whatever it is, it's the PyTorch model or whatever it is, but now when it is ported to these particular accelerators, they behave differently, right? So now in runtime, how do you know, like should I run my exception on an NPU or should I run it on GPU? So everybody, if you want like high throughput, then you say that you are always wanting to run on NPU. But then if you see here, right, the accuracy also is very low. For tiny YOLO, the accuracy is around 10% difference if you run it on a VPU versus if you run it on a NPU, right? So now you have this trade-off between the accuracy, the throughput that you achieve, and also the power that you consume on the same hardware, right? So now this is something that how do you kind of do on a runtime, that when you do not know, because the application arrival is not known to you, but you know what kind of applications that can run on this board or the SOC, right? So now what we did is, how do we try to understand that when multiple applications are coming together for execution, what we want to do, right? So first we had to build some model, right, to understand like how we get degraded when somebody is co-running with me, and what will be, because there is no change in the accuracy, but there will be change in the throughput, right? Because accuracy will not change compared to an isolation run. It will be the same because the same model you are running. What will change? The change will be only in terms of the throughput that you achieve, right? So now in this case, what we did is we tried to do performance and power prediction models, right? So basically what we did is we tried to use this runtime counters, which is the performance counters available in the hardware, which will try to based on the activity of your application, those counters will get populated, right? So these are very what you say counters available with most of the hardware that will try to characterize the compute's activity as well as the memory activity in terms of L2, memory accesses, and so on and so forth, right? So based on these runtime counters and based on the static property of your application, we kind of built a profiling data set that will try to build, like say for example, if this particular model, so in our example we had exception, YOLO and inception, right? So if exception and YOLO are running together on an NPU and GPU, so if exception is running on NPU and YOLO is running on GPU, what will be the degradation YOLO will predict, I mean YOLO will get, and then what will be the degradation that the inception on the NPU will be subjected to, because YOLO is running along with it, right? So based on some profiling, we had already got these things, and in runtime we want to invoke based on the application that is running on the system at that point of time, because we do not know, like in this case, right, if you see, you are having multiple things. At what point, whether you want to invoke a audio application or you want to make a text, given an image, you want to get the caption of that image and so on and so forth. You do not know what your application is going to be, but you know from this set of applications only, your that particular time you will be able to get the application on your SOC, right? So based on that logic, what we did is we first built this profiling module and profiler, and then we tried to use this because you have so many features in your hardware counters, right? How do you know what is the best feature to build your prediction model, right? So now we made use of this genetic algorithm to understand what are the best features suitable for modeling that contention, modeling the degradation, performance degradation, and we use those features, and we try to train the models that can be used in the runtime, right? So in the runtime we have this enhance coming, and then we have our algorithm checking what hardware is available, whether some hardware is already busy, like if your NPU is already used by some other application, you can't use it till that application is over, right? So now should you wait, or do you want to find the next best hardware without, because you are also getting the importance from your user. So now you have three different metrics. One is the execution time, another one is the power, another one is the accuracy drop. So this alpha, beta, gamma is the user specified input. That is like I'm okay by losing this much accuracy, but I don't want to compromise on my latency. So this alpha, beta and gamma tells the relative importance of that particular metric that you want to optimize for from the user's point of view, right? So based on this, we had formulated as a optimization problem where you are minimizing this. You're minimizing the execution time, you're minimizing the power, and you also minimize the accuracy degradation. Like you want to keep as close as possible, but what is the possible degradation that you're tolerate based on the whatever the input your user is giving. Okay, I am able to tolerate 2%, I'm able to tolerate 10% in latency, I'm okay, but then I cannot tolerate any degradation accuracy. I want the maximum accuracy possible. That can be specified by the end user of the application. So based on that, we will be able to kind of get the possible so in runtime, based on the already executing applications and based on invoking our prediction models, we will be able to know like what will be the possible degradation. So accordingly, we will be able to map. And then, so in this, we are only able to do two accelerators at parallel, because we are not having models for more than that. So at any point of time, we are able to only use two of these available accelerators, and also our like I said, the SOC is very low resource, right? So it cannot, if you try to handle more than, or like all the hardware together, all the accelerator together, you have problem in this heating up and other things. So for these experiments, we tried only using at any point of time. So that is the reason you're checking the status of hardware and make sure that not more than two of the accelerators are used at any point of time. That is what this work is about. So here we could try to, because we are trying to balance between these three objectives, right? Throughput, accuracy and power. So we were able to get some good balanced points without having like penalizing any one very highly. Like we are not dropping so much accuracy, at the same time we are able to save power as well as not have the completion time as large as possible, right? So we are trying to do as minimum complete time as possible, and then minimum power as possible, and minimum accuracy drop as possible. So that is possible with this algorithm, right? The last one, so far we had seen about the characteristics in the environment, the characteristics of the hardware, the characteristics of the application, right? So now the last one, what we're going to see is how can you use the changes in your input to orchestrate your execution in a different way or in a better way, right? Say for example, what I was trying to tell here is like you take CFAR 10 data set, right? So you have 10,000 images there. So all of these networks, ResNet 8, ResNet 14, ResNet 20, all of them have been trained to identify all of those images, right? So now, if you see out of these 10,000 images, 6,320, which is like 63% of the images, can be identified with a small model. You don't need ResNet 20 for these 63% of images, right? Only for this 5% of images you require the larger model, which is ResNet 20. So why do you want to use ResNet 20 all the time, right? So is it possible to find out based on the input characteristic, okay, for this set of images or image, ResNet 8 is enough, we don't need a larger model, right? So if you dynamically able to identify that, and if you are able to dynamically dispatch to the correct model based on the input feature, you are able to get much more better accuracy at a much lesser operational cost. So this is like mix and match of, so you already there is this mixture of experts kind of a thing, right? You have multiple experts, and then depending on the data set, this is somewhat close, but then here we are not training new experts, we are using the pre-trained models already available, but then dynamically how do you orchestrate them based on the changes in your input, right? So this is what we wanted to do. So for this, what we tried to do is, okay, so I didn't go about much about the details, but yeah, so the higher level idea is, so generally when you are training your CNN, right, you have your loss function is just one thing, which is to maximize the accuracy. You're not worried about anything about the computational intensity or the flops used, right? So in our case, what we're trying to do is, we are trying to have this dispatcher. So we are trying to design this dispatcher, because the dispatcher should know, right, based on the input features, where it should dispatch to, right? So or which is the ideal model it should dispatch to, right? So for that, we have defined a custom loss function that has two things. One is the accuracy maximization objective, another one is the minimization of the compute flops. So when I'm saying minimization of compute flops, what I mean is, so ResNet 8, if you see, right, it takes only 6 flops per image, whereas ResNet 20 takes around 22 flops per image, right? So when I'm saying, if I'm using most of my models out of the 63% of images, if I correctly give it to ResNet 8, because it is able to correctly identify, only the remaining 5% I'm able to use it properly. So this is the role of the dispatcher, right? If I'm able to do this, I will be able to save like 60% in the mflops that I use if I use completely ResNet 20 for all the images, right? So that is the thing our dispatcher is trying to do, and for that, what we are trying to do is, okay, because CNN is already learning the features about the input, right? So why can't we reuse the features? So basically, anyway, we are trying to use these pre-trained models for execution, right? So we will try to use the smallest model, and then take all the layers before the fully connected layer and use that as the backbone extractor, and make those features. Using those features, we try to learn which is the most suitable model for that particular input, right? So we don't reuse, we already reuse the computation. So only the extra thing that this dispatcher is doing is one fully connected layers work. So that is a small overhead in compared to the savings that you are getting, right? So basically, what we are trying to show here is, we are able to beat the SOTA models by properly orchestrating them. So one, there were certain problems that we had tackled, but I'm just showing you the final result, right? What we are trying to see. If you see here, right, so these are the green points are the SOTA models, right? So in this case, you are having ResNet 8, 14. So this is on CFAR 10. We also have the data on CFAR 100 and ImageNet. So what we are able to see is, so these are the accuracies that you are getting by using this VGG16 always. So if you use VGG16, you get somewhere around 92%. But we are able to use much lesser mflops, but still achieve similar, accuracy at much lesser power, right? So if you see here, this is the accuracy and this is the power consumption. So if you use always VGG, you are using this much power, but we are almost like 10,000 milliwatts lesser than the state-of-the-art models that you are using. So that is what I wanted to say.
1 minute left.
Yeah, thank you so much. Yeah, I am done.
Okay.
So we also did on VIT, and so we also did on something else. But yeah, due to the interest of time, I am skipping all this. Okay, thank you so much.
Thank you, Rajni. Questions? Questions, anyone? So
No
one
questions.
quick note before we break for lunch. Please don't go out. We plan to take a group photo before we break for lunch. Okay?
No
After
questions, or you're very bored.